Today, we're going to break down two of the absolute bedrock concepts in computer science: arrays and linked lists. Now, that might sound a little technical, but trust me, this is the hidden logic that makes so much of our digital world even possible.
I mean, have you ever stopped to wonder how your phone can search through thousands of your contacts and pull up the right one in like a split second? The secret sauce is something called a data structure. And really, that's just a fancy term for a specific way of organizing information so a computer can work with it super efficiently.
All right, so to really get how this works, let's start with the one you probably already know, even if you don't realize it. It's the most common data structure out there, the array.
The best way to think of an array is like a perfectly organized bookshelf. You've got a bunch of slots, and every single item sits in its own numbered spot, right next to its neighbors. The key here is that they are physically next to each other in the computer's memory. So if you know you want the item in slot number 5, you can just jump straight to it. No fuss.
Because of this nice, orderly structure, arrays are really good at a few core jobs. You can read through them from start to finish, you can add or delete things, search for a specific item, or update something that's already there.
For example, let's look at what's called traversal. It sounds complicated, but it just means visiting every single item in order. Because everything is in a neat little row in memory, this is incredibly fast. The computer basically just takes one step to the right to get to the next piece of data. Simple.
But, and this is a big but, an array's greatest strength, that rigid, predictable order, is also its single biggest weakness.
So let's make this real. Imagine we have this list of user IDs, and we're keeping them in an array, all sorted in perfect numerical order. Looks great, right? Clean, organized, easy to read.
But then a new user signs up, and their ID is 1005. Uh-oh. To keep our list nice and sorted, that new number has to slot in right between 1000 and 1010.
And this is where we hit what's called the shifting problem. You can't just magically make space on the bookshelf. You have to physically move every single book that comes after that spot. So you have to pick up 2040 and move it one space over, then pick up 2000 and move it, then 1050, then 1010. It's this painstaking process of shuffling everything down just to create one empty slot. Now imagine doing that with a list of 1 million users. It would be an absolute nightmare, incredibly slow and computationally expensive.
So if arrays are a pain for this kind of thing, there has to be a better way, right? Well, there is. And this is where our second data structure, the linked list, comes in and provides a really clever solution. Okay, so if an array is our bookshelf, where everything is side by side, I want you to think of a linked list as more of a scavenger hunt. Each item can be stored literally anywhere in the computer's memory. It doesn't matter, because each item holds a special clue, what we call a pointer, that tells you exactly where to find the next item in the chain.
The magic ingredient here is something called a node. And a node is super simple. It just holds two things. First, the actual piece of data you care about, and second, that all-important next pointer, which is just the address of the next node in the scavenger hunt. And the whole list starts with one special pointer called the head, which just points you to the very first clue. So that's the theory. But how does this whole scavenger hunt idea actually solve our massive shifting problem? Well, let's just watch it happen. It's actually pretty cool.
So here's our existing list, a little chain of numbers. We've got 10, which points to 15, which points to 7. Pretty simple. And our mission is to add the number 13 right at the very front.
Step 1, we just create a brand new node and pop our data, the number 13, inside of it. Right now, it's just kind of floating out there in memory, totally on its own, not connected to anything. Okay, now for the first clever bit. We take our new node, the 13 node, and we tell its next pointer to point to what used to be the first node in the list, the one with the number 10. And just like that, we've created the first link in our new longer chain.
And now for the final move. We just change that main head pointer for the whole list. Instead of pointing to the 10 node, we just tell it, hey, from now on, you point to our new 13 node. And bam, we're done. The 13 node is now the official start of the list.
Now pause for a second and think about what we didn't do. We didn't move the 10 node, we didn't move the 15 or the 7. There was zero shifting. All we did was change two little pointers, two little addresses. It is unbelievably fast and efficient. So after all that, which one's better, the array or the linked list? Well, in programming, the answer is almost always the same. It depends. It's all about picking the right tool for the right job.
And here is the fundamental trade-off. Arrays, our bookshelf, are amazing if you need to read data a lot, because you can jump straight to any item instantly. but they are awful if you're constantly adding or removing things in the middle. Linked lists, our scavenger hunt, are the exact opposite. They are fantastic for inserting and deleting elements. It's super fast. But if you want to get the 500th item in the list, well, you have to start at the beginning and follow the chain 499 times to get there, which is not fast.
And that leaves us with a really fascinating puzzle for developers, doesn't it? If the bookshelf is fast to read but a pain to change, and the scavenger hunt is easy to change but slow to read, what on earth do you do when your app needs to do both things really, really well? Well, the answer to that leads us into a whole world of even more advanced data structures. And that sounds like a story for another time.